and also the temperature went down very low. Okay, and then we got a lot of power outage. Okay, during those days. You guys were born already. I'm pretty sure. Okay, 2013 or 2014. It's one of the worst winter I've realized. Okay. So this statement make is that the temperature increase. Okay, you get compression. Temperature decrease, you got tension. Okay, so temperature increase, compression. Temperature decrease, you get tensile. Okay. So I want you to just remember this statement for thermal stresses. Okay. So always remember, important thing to consider. Okay. There is no stresses okay, associated with temperature change when there is no restriction in motion. Okay. So what do I mean in this? What do I mean? Okay, so I will give you an example. Okay, I'll give you an example. So if one end of your beam is built in and the other side is free to move like this. Okay, one end is built in. And the other side is free to move. Right over here is free. So either there's a change in temperature, okay. In this case, where you have change in temperature, no stresses will be generated. Because if I call this point A and point B, this is because point B is allowed for free extension or contraction. Right? So that is why in Canada, especially in Canada, when we design a bridge, right, one end is pinned, the other side is on a roller. Right? Why? If I have a transformation over here, and this is my X and Y, right? And this is our rotation in Z. When it's pinned, X motion is equal to 0, Y motion is also equal to 0. When it's on a roller, right? X motion is not equal to 0 anymore. Why? Is because it can go left and right, but Y is equal to 0. You want to support the load, okay, prevent it from swinging downwards. So for this reason, that's why a lot of bridges, one end is fixed, the other one is on the roller, so that when there's a temperature change, there's no stresses. So our temperature in Canada in summertime can be 40 degrees, right? And then in the winter time, within a day, you can change in 20 degrees. Okay, that's why most all bridges, one end is pinned and the other end is on a roller for that reason. Okay. Now, coming back to our example down here. Now, if both ends, okay, now if we use the same rod, okay, we use the same rod, right? Now, both ends are built in. You restrict motion now. Right? So one end, point A, and point B. So both ends are built in. Okay, the other end is also built in. Okay. Now, if temperature increase, we know that the structure wants to deform outwards, right? Temperature change, it wants to go outwards. Yes or no? Right. So this is increase in length, right? But point B is there, right? You don't allow it to move. So for it to prevent it moving, okay, RB will be pushing it back, right? So RB, what you see down here, RB will generate a compressive stress, right? You can see now, right? So once you have a temperature increase, it wants to grow, okay? But at point B, you have a wall down there, and the wall will be pushing it back, okay? Or the wall will be creating a reaction known as RB. So RB will generate a compressive stress. This is a temperature increase. Interesting, isn't it? So now if we have a temperature decrease, okay, we have a temperature decrease now. So again, the same thing. Point A, point B, okay? So both are built in again. The other side is also built in. Okay, so now you have a temperature decrease. All right, so what will happen is the structure now wants to contract. Okay, so I'll draw different color. Okay, it wants to contract. Okay, so it wants to decrease in what? Decrease in length. Right, it wants to decrease in length. However, at point B, right, the built-in wall does not allow it to what? String. Okay, so it will pull it what? It will pull it back. So it will pull it back in this direction. So this is my RB. You pull it back to the wall, right? It wants to reduce, but you pull it back to the wall because it's built in. You cannot move. Okay, right?
Tensile
you cannot.
stress?
Yes.
Would that be tensile stress?
Yes.
Right?
So that is why, okay, RB will generate a tensile stress. Okay, that's why we make this statement, right? That's why we make this statement. Now, when there's a reduction in temperature, there's going to be a what? Tensile stress, and this is the reason why. Okay, this is the reason. Okay, so now I'm going to introduce you to a new formula. Okay, just an extra formula for what we're going to do down here. Okay, so the analysis is still the same. Okay, in terms of you allow the structure to change in length, and then you push it back or you pull it back. Okay, you push it back or you pull it back. So thermal induced deflection. Okay. can be determined by deflection due to temperature is equal to alpha delta T, and then we have L naught. Okay, so this is the formula that we are going to apply. Okay, where delta T is deflection due to temperature change. Okay, and then the units can be meter or inches. Okay, and then delta or alpha is the coefficient of thermal expansion okay, deflection, thermal deflection of thermal expansion. The unit is 1 per degree C or 1 per degree Fahrenheit, depend on whether are you dealing with temperature in degree C or Fahrenheit. And delta T is the change in temperature. And the change in temperature, delta T, is always T1 minus by T0. Okay, T1 is the new temperature. T0 is the reference or original temperature. So if T1 is equal to 80 degrees, right, and T0 is equal to 25 degrees C, right? So delta T is equal to T1 minus T0 is 80 minus by 25. So this is equal to positive 55 degrees C. Now, if T1 is equal to minus 60 degrees C and T0 is equal to 25, right? So the change in temperature is equal to T1 minus T0. So it's equal to minus 60 and then minus 25. This will be equal to minus 85 degrees C. Okay. So what you see over here, that when that's the case, the deflection due to temperature is what? Positive. And over here, the deflection due to temperature is what? Negative. Right. So in terms of stresses, this will become compressive. I've shown you why already, right? And this is, you get tensile. Okay. So I'm going to, and any more to add in? Did I define? Oh, sorry, I did not define L naught. L naught is the original length. Okay, L naught is the original length. I'm going to show you the solution procedure again. Okay, so solution procedure. Okay,